Our notes today start with the question, what do you already know about functions? So I guess that should be a question. If you haven't already done this, I would encourage you to pause the video and try to think about how to fill these in on your own, because you've seen functions over multiple years now. It's just that we're going to be expanding on what you know, and they'll become incredibly important through all of the rest of math. So think about what you already know, and I'll just put a couple of things here once you're ready to unpause. So a definition of function is a relationship between two things. We'll call them variables. But more importantly, I think of it as a characteristic being that it's like a machine with inputs and outputs. Inputs and outputs. One of the most important characteristics of it is that each input has exactly one output. So a way of thinking of examples of this would be like vending machines. So a normal vending machine, like you have for, say, candy or Cokes, has all of these, say candy or food, has all of these items in here, and they each have a different code. So this one might be A1, and this one might be A2. So an example would be vending machine, in that if I put in money and I pick A1, I'm going to get that chips, whatever it is. So A1 gives me chips. A2 gives me Snickers, or whatever it might be. So each letter, each code I put in gives me a specific item. A non-example might be a different kind of vending machine. So I don't know if you've ever seen the ones that have all the little prize toys in them, but they're in little capsules. So I don't know what I'm getting. I put in money, and out comes a capsule, but I don't know what's in it. So we'll call this a capsule machine. So I repeat the same input over and over. I put in a quarter or a dollar or whatever. I get out a capsule with a toy. I get another capsule. It has a different toy. I get another one. Maybe it's a repeat of the first toy, and I'm frustrated because I want all the different ones. But the normal vending machine where I know what I'm getting out, that is like a function. And this one is not a function. So we're starting off our review of functions with remembering how to identify them. There's multiple ways that we can see functions represented. We can see them represented in ideas, like with the vending machines, or we can see them represented in mathematical ways. So these are functions as drawn on a graph. And it says that, do you remember the vertical line test? So sometimes we call that VLT. And it says that a way of seeing that each input has one output is to check, remember, inputs are just X values and outputs are Y values. So when I look at the X value 1 and I look at what the Y value is, it's 1. When I look at the X value 3 and I look at the Y value, it's 1. I'm looking at this graph here if you couldn't see, sorry. And I look at the X value 5, the Y value is 1. So each time I pick an X value, there's only a single corresponding Y value that is the output. So a way of thinking of that is just look at one X value. Oh, I have to try to draw straight. That's tough. So at X equals 1, then there's only one spot where I cross the graph. At X equals 3, there's only one spot. So that's a way of representing visually that for each of these X values, which should be a straight vertical line, there's only a single Y value where I cross the graph. Let's compare that to this left one on the next row. If I draw a line here, I cross this graph at 1, 2, 3, 4, 5 points. So when I put in the x value, when x is equal to -2, y could be, it looks like 0, -2, 4, lots of numbers, right? So y could equal a bunch of different things, not just a single value. So this one would not be a function because there's different outcomes with the same x value. The next graph, if I look at -3, I could have the values -2 or -3. So this is not a function because multiple values come out of it. And it doesn't matter if every x value has different y values. A single x value where there's a repeated y value kind of disqualifies it from being a function. So going back to our vending machines, let's say that for fun, the company that made the vending machine made A3 be a mystery thing. So now when you pick A3, it's hidden behind a little screen, and you don't know, are you getting candy? Are you getting chips? Nobody knows. So this vending machine would no longer be a proper function because one of the options for the input can give you different outputs. Or say it's just a mystery flavor, like Lay's makes a mystery flavor bag and you don't know which one you're getting. Okay, the next one, it goes up and down and looks all squiggly. It's not a nice straight line, but anywhere I go through and draw my vertical lines, I never cross this graph more than once. So this one is a function because it passes the vertical line test. There's nowhere that I can pick that I will get multiple y values. Same thing with this next one. Anywhere I pick, I only get a single y value. So this one is a function. And of course, the first one, the nice straight line, was a function as well. Let's look at these next ones. If you have not already looked at them, I would pause and make sure you can identify them. So the first one is a straight line. Straight lines are always going to be a function. The second one is squiggly. We can fail the vertical line test in multiple places, so it is not a function. The circle, we can fail the vertical line test in multiple places, so it's not a function. And then this last one is a little tricky. So if you think about drawing a vertical line right here, I cross this line in infinite places because it's right on top of it. So if I pick 2.5, I have no idea what value is coming out. So when x equals 2.5, y equals everything. So y equals like all real numbers. So that one is definitely not a function. It fails spectacularly. So some new vocabulary that we're applying to this idea. You've seen this multiple years now, but we're going to be using the vocabulary. The inputs come from a set called the domain of the function, and the outputs are a set called the range of the function. So we've talked about inputs and outputs, but you probably haven't talked about the vocabulary domain and range. So remember, domain is just all the inputs. So in terms of like a graph, that would be all of the x values. And the range is all of the outputs, or all of the y values on a graph. So when we have this relationship, another vocabulary that it doesn't say here, it is the output is a function of, so is a function of the input, or that's often written y is a function of x. So if you ever see different letters, so if you have like, I don't know, the input is called A and the output is called B, it would say B is a function of A, and that would tell you that B is the output and A is the input based on how this statement is written. So it would be really weird and probably a typo, but if it said x is a function of y, then in that case, x would be the output and y would be the input, which is kind of strange. But you do have a question of, in higher math, not in right now, of whether something is a function when it's inverted. So for example, we would look at on these graphs up here if we pass a horizontal line test to know if x is a function of y. We're not worried about that yet, but in Algebra 2 maybe. Okay, so this is a different representation. We looked at graphs. These are called mapping tables, and they just list the values of the inputs and outputs. When we use these, there's a couple of important things to keep in mind. So these values always go in ascending order. That means increasing. And there are no repeat values. So if something repeats, instead of writing it twice, we just draw two arrows from it. So in this first example, 2 maps to -1. 2 also maps to 8. So that means for this input of 2, there are two different outputs, so this is not a function. In this one, 0 can map to 1 or 3. So imagining that on a graph, that means when x is 0, y could be 1 right here or 3 up here. So we would fail our vertical line test. So this one is not a function either. The next one's a little different. So 2 goes to 4 and 3 goes to 4. So thinking about that again on a graph, when x is 2, y is 4. When x is 3, y is 4. Well, that's fine. That doesn't fail the vertical line test. It would fail a horizontal line test, but we're not talking about that. So this one's totally fine. I can draw one vertical line through 2 and only hit a single number, and one vertical line through 3 and only hit a single number. So this one is a function because it does pass the vertical line test based on the data that we have. And the next one, a lot of things go to 7, but each input only goes to a single output. There's no branching on the left, so this is a function. So imagine if we wrote a mapping table for this very first example way up here that was a horizontal line. It would show every single x value goes to a y value of 1. So we would have 1 here, and we would have like -5, -4, -3, -2. They'd all go to 1, and that's okay. That's still a function. It passes the vertical line test. So visualizing these in terms of what they mean on a graph can be really helpful. The same thing if you're given a list of ordered pairs. So these are all points on a graph. So again, imagining we're looking for the same input leading to a different output. Well, if we don't have any repeated inputs, I have -1, 0, 2, 7, well then it's impossible for me to have one input go to two outputs because I never see one of them twice. There's no repeats. So this one is a function. And again, if I think about a graph, -1, -2, 0, 1, 2, 4, 7, 7, like all of these are on separate vertical lines, so there's no way that it could be disqualified. And it said you can create a map. I would prefer that we actually think of a graph instead of a map. I find that to be more simple and visual, but you can create a map as well. So you could write this, remember that we write them in ascending order, so -1, 0, 2, 7, and then the other half of the map would be -2, 1, 4, 7, and they just map straight across, so no problems there. This, by the way, it says is called set notation. We'll be seeing quite a bit of that when we're referring to what we call sets of numbers. A set is just multiple numbers or multiple items. In this case, it's multiple ordered pairs. So we have the point -1, -2, 0, 1, 2, 4, and 7, 7. They're contained inside of these things that we call curly brackets. So they kind of go out to a point and then back in. And they just are a visual indicator that what's in there is a set of items, which is either numbers or objects. And we'll talk more about those as we get into domain and range, because those are a way that we list those as well. All right, the second set, I see I have 1 maps to 1, and 1 also maps to 2. So that's no good. That's going to be failing our vertical line test. Here we have 4, 1, 0, 1, 4. Okay, I saw repeats. Here 1 goes to -1, 1 goes to +1. That's 2 different values, so this is not a function. I will talk about, since this is changing direction, if you wanted to write the map properly for this, remember that we write the x's from smallest to biggest in ascending order, so that would be 0, 1, 4. And then our outputs also from smallest to biggest. So I have -2, -1, 0, 1, 2. And then I would connect them up. So 0 only goes to 0. 1 goes to both -1 and +1, which is our problem. And 4 goes to -2 and +2, which is another problem. So not a function. The next one, I have -3, -2, -1, 0, 1. There's no repeated inputs, so this, as far as we know from these points, is going to be a function. The next one has 5, -1, -5, no repeats. 1, no repeats. 5, there's a repeat. So we had 5 goes to 1, and 5 goes to 3. So that's not a function because 5 went to 2 different numbers. All right, given a table. So tables are a lot like a list of points. They're just written in a different way. So these are still ordered pairs. Think of this as being 4, 3, 5, 4, 2, 5, and 4, 6. When we write a table, the domain or the x values are always on the left or on the top, depending which way the table's going. If it's a vertical table, x is on the left. If it's horizontal, x is on top. It's just the order that we read in. So we read left to right, and we read top to bottom in the English language. So this table has 4, 5, 2, 4. 4 goes to 3, and 4 goes to 6. That is not a function. In this one, 2 goes to -1 and 2 goes to -1. So that one's kind of tricky because 2 showed up twice, but these are the exact same point. They're not 2 different points. So this one actually is a function. The next one has no repeated x values, so it's a function. This one has no repeated x values, so it's a function. And the last one has 1 repeated x value, but again, it's the same exact point, so that does not disqualify it. Next, we have a real-world situation. So we're going to make some money babysitting. We're charging $12 per hour. Is this a function? What would our variable be? So if you haven't done this, think about it, pause for a second, and then I'll go through it. All right, so this would be the number of hours that we babysit. That's the thing that varies or changes, and I would call that h if I were writing an equation. Can I complete the table? Yes, I can complete the table. So this is going to be the hours that we worked, and this is going to be the money earned by working. If I work 0 hours, then I'm going to make $0 because, yeah. If I work 1 hour at $12 per hour, I make $12. Another hour, I get 12 more, then 12 more, and so on. So this is a nice straight line with a slope of 12. The equation would be y, that we're using y and x, I guess. I would use h and m maybe for money. I don't know. So y equals, so we have no money at time 0, so that means our y-intercept is 0. And we make $12 per hour, so that's 12 times x. So that's linear, and linear equations are functions. All right, so that should hopefully be all review. Then we're going to get into some new things now with functions, the first of which being what we call function notation. So you've written equations as being like y equals 12x. That doesn't actually show that y is a function of x. They're two separate variables. So we just have a different way of writing functions in what we call function notation, where we put f of x equals 12x. So this f of x has the same meaning as y. It's still our output, but what this name does is it tells us that it's an output where x is the input. So we know that x is the input and f of x is the output. And it doesn't have to be f of x. We could write g of x equals 7x minus 3, h of x equals 2x. All of these are functions of x. What matters is the part in the parentheses. And remember, we read it f of x. So a function of x. And it doesn't have to be f, it can be any letter. So we have the equation y equals 9 minus 4x. We can use f to name it. So f is basically just a name. The important part is the parentheses part that says of x. So it's coming from that variable, and it's an output related to that input. So this leads us to a topic called evaluating functions. Evaluating just means substituting a value. And we've done that before to check our answers when we were doing simple equations before. So if I have this equation, which is f of x equals 9 minus 4x, and I want to find f of 2, well, notice what we did here. We replaced x with 2. So we're asking, what is the output when x is 2? So to find that, we literally do the same thing. We replace x with 2. So wherever the x was, we're going to substitute the value of our input, which is 2. So we have an input of 2, and our output, f of 2, is going to be 9 minus 8, which is 1. So notice in this part, we're not solving anything. We're just simplifying or evaluating. So evaluating is also simplifying. And when we do that, we follow our normal order of operations. We're not doing anything backwards. We're going forward through the order of operations to evaluate what f of 2 is. So we'll go through some more examples. I know that's new and can be uncomfortable at first, but it's pretty easy once you practice it a little bit. So given f of x equals 7x minus 1, find f of negative 2. So f of negative 2 is equal to 7 times negative 2 minus 1. So again, this is, lost my highlighter, this is where x was, right? It was f of x, and now it's f of negative 2. So x became negative 2. So f of negative 2 is equal to negative 14 minus 1. So f of negative 2 is equal to negative 15. So the common misconception is that f parentheses negative 2 is a multiplication operation, but it's not. It's saying f of negative 2. So it's saying negative 2 is the input to the function f. So negative 2 goes into f, and out comes negative 15. So on a graph, that means there'd be a point at -2, -15 way down here. For the function g of x equals x squared minus 4, what is the value of g of -5? So g of -5 is equal to, we put -5 where x was, and we square that, minus 4. -5 squared, remember that means -5 times -5. When we multiply that, we end up with a positive number because a negative times a negative is a positive. So we get 25 minus 4. 25 minus 4 is equal to 21. So g of -5 is equal to 21. So this is something that is a lot simpler to deal with when we're not working with calculators. When you put in the calculator, because you will use calculators at some point, if you put in -5 squared, then the calculator is going to tell you that that's -25. The reason it does that is it's following the order of operations. So it says this negative is multiplying by the 5, and this 2 is an exponent of the 5. So when it evaluates that, it does the exponent first, and then it says you have negative times 5 squared, which is -25. In reality, if you type this in the calculator, you have to type it as -5 in parentheses and square it, and then the calculator will tell you that it's 25. The reason for that is it groups together in the parentheses, so it's squaring -5, not making 5 squared negative. So hopefully that won't be an issue because we're not using calculators very much. But if you do ever type a negative squared into a calculator, it will give you a misleading answer because it is strictly following order of operations. And what you told it is to make the negative of 5 squared because the square happens before the negative does. All right, the next one, given h of x equals 5x minus 1, what is the value of h of x equals 9? That's not written super well. I probably need to update that. So what is the value of x that makes h of x equal 9? So here we're not given a value of x. We're given a value of h of x. So h of x equals 9, meaning that 9 in this case is an output. And we can recognize that in a couple of ways. It's not in the parentheses. So a common mnemonic or way of thinking of it is if the number is in parentheses, it's an input. And if the number is outside of the parentheses, it's an output. So this number says h of x equals 9. The other way is just to remember h of x is right here. So before we were replacing the x part. This time we're replacing h of x. So that one can be a tricky thing to keep straight, but we're replacing the output with 9. So we're going to put 9 on the left equals 5x minus 1. Now this problem we need to solve. We're not just simplifying it like we were when we put in an x value. Now we need to do our inverse operations. So we would do 9 equals 5x minus 1. We would add 1. 10 equals 5x, divide by 5. X equals 2. Or 2 equals x, and then I would reverse it to put x equals 2. All right, this says if f of x equals negative x plus 2, find x if f of x equals 6. So this one is worded better. It says to find x. So again, we're given the output. So f of x equals 6, so we're going to put that here. So 6 is equal to negative x plus 2. Then we're going to subtract 2 from both sides. And we get 4 equals negative x. And then we're going to multiply or divide by a -1. And we get -4 equals positive x, and we'll write the answer as x equals -4. There we go. So keeping straight whether you're evaluating from an input or an output is really important in these problems. And you just have to kind of practice it and get used to seeing which is which. So there's some practice problems here to do in the notes. I'm not going to go through all of those. I'll go through the check for understanding, and then we'll close out the video there. So the function f is given by f of x equals 3x minus 1. Work out the value of f of 7. So the 7 is in the parentheses. It has replaced x, meaning that we're going to substitute 7 where x was. So that means I have 3 f of 7 equals 3 times 7 minus 1. That's 21 minus 1. So f of 7 equals 20. The function g is given by g of x equals 2 times x plus 5. Find g of -1. Oh, I'm really glad we have this example. That's good. So -1 is replacing x. Let's write that. So g of -1 equals 2 times -1 plus 5. Remember that since we were given an input, we are following PEMDAS in forward order, which says do what's in parentheses first. So I don't want here for you to distribute this 2 to these two parts. That's terrible. Instead, simplify what's in parentheses first. -1 plus 5 is 4. Then multiply 2 times 4 is 8. So that's g of -1 is equal to 8. And then for our last one, h of x is 5 minus 8x. If h, I guess this is x. I guess it could be a, that's fine. So h of something equals 1. So 1 is outside the parentheses. So that means 1 is replacing h of x. So we would write that as 1 equals 5 minus 8x. I guess 8a, because we're substituting a for x. But whatever, it's just letters. So then we would subtract 5, and we would get -4 equals -8a, and divide by -8 to get the a by itself. We get 1/2, which is positive because we divided negative by negative, and then we get just a. And that's it. So that's where we'll end on this one. This is something you really do have to practice, and that is really important and will continue to show up throughout all of high school math. So definitely work on it and get it down. Don't just kind of glaze over it and think it won't be important.